Hello and welcome, honors students. Today we're going to begin chapter 16. So the upcoming test that we'll have next Thursday will be over chapter 15.1, 15.2, 15.3, 16.1, and 16.2. So I put the study guide already on Moodle for you, so you should have at least seen it or the opportunity to print it. Now on Tuesday, I will have a virtual lesson where I will go through that with you. On Monday, I will have another virtual lesson for us, and it will be 16.2. That is all we're going to have within chapter 16. As you can see here, is this introductory slide. It's 16.1 through 4, but we will not have time for that. We will just do 16.1 and 16.2. So let's get started. So here it says, how can you grow a tree made out of crystal? Well, this is really about what we did right before Christmas. If you remember, we took sodium borate and we heated up some water and we added quite a bit of sodium borate into it. And what it did was dissolve at that near boiling temperature. And then we put inside of it one of those pipe cleaners, different shapes, and we allowed it to cool. And what happened when it cooled, we had the formation of the crystals, and that's what you see happening right here on this, the formation of the crystals. Why? Because as the liquid cooled, it would not hold so much of the solute, and because it was an ionic compound, it formed these crystals. And that is what is going on here in this. So we're going to talk about solution. Solution chemistry is very big area, big subject, a concept in and of itself. So we're only going to really touch the basics of it. So what factors affect how fast a substance dissolves? So think about that. You have a cup of coffee and you want to put some sugar in it. It's hot. So you can put that in, stir it up, and it's going to dissolve actually quite rapidly. Think about this. What if you had a sugar cube and you dropped it into that hot coffee? Now, if you stir it, you're going to get it to start to break up, and then over a little bit of period of time, that cube will dissolve and it'll be gone. Think about this. What if it was cold and you put the sugar in it? Would anything be different? And that's what we're going to talk about, some factors that affect, and there's actually 3 factors that affect how quickly something will dissolve. Now, in order for it to dissolve, remember, the substances have to be compatible. It has to be like, so it has to be polar with a polar or non-polar with non-polar. But we're not really talking about that aspect of it at this point. We already learned that. We're talking about factors that will affect how quickly something will dissolve. So let's talk about that. Here's what I just said. The composition of the solvent and the solute determines whether or not it will actually dissolve. So remember, the solvent is doing the dissolving and the solute is what's being added. So if you had a cup, whatever liquid was in here, that's your solvent. And whatever you are going to add in, that is the solute. And please keep that in mind. So there are 3 factors that affect how quickly something will dissolve. Number 1 is agitation. Number 2 is temperature. And number 3 is the size of the solute. So you already heard me talking about the coffee and having to stir it. And we talked about hot and cold coffee. And then I talked about a cube versus the granules. So that is what we're going to look at, a little bit of information on each one. But in your notes, you should put there are 3 factors and you should have each one of these written down. And what you'll do is just put a little bit of brief information about each one. So let's begin with agitation. What is agitation? It's exactly what it sounds like. It is stirring or shaking. Affects only the rate at which a solid solute dissolves. It does not influence the amount that will dissolve. You're only going to get a certain amount. We won't have time to study it in this course. I apologize on that with just the time. It's called KSP. If you take you take AP chemistry with me, you will learn about KSP, that's equilibrium constant, and molar solubility. We'll learn all those things. However, we're just understanding that if you stir or you shake a cup of tea or coffee or just water with something in it, you are not going to influence how much it will dissolve. That's determined by other factors. What you'll change is how quickly it will dissolve. An insoluble substance remains undissolved regardless of how vigorously you shake it. If you had oil in there and water, you can shake it as much as you want. It'll just blend it all throughout, and then it will form its layer. And if it's something that's non-soluble, say, for example, silver chloride, which is got a very low solubility in water. A little bit dissolves, we mentioned that previously, but not much will. So if you shake it, it doesn't matter how much you're going to shake it, that little bit will dissolve and then nothing else will, and the rest will just settle out of the solution. But if you have something like sugar or salt or potassium chloride, those things will dissolve faster if you stir it or you shake it. It won't dissolve more of it, it'll just dissolve, but will dissolve faster. Temperature. Now, temperature does have an effect. Most of the time, the higher the temperature, the more soluble something will be in it. So at higher temperatures, the kinetic energy of the water molecules is greater. We learned that already, so the molecules move faster. The more rapid motion of the solvent leads to an increase in the collisions and thus allowing it to dissolve. So we talked about the process of solvation. We learned about that in the last section. So that's the process of the water molecules encompassing and encircling an ionic compound and then pulling it apart. And the hotter a substance is, the more rapid the movement of the particles. So with the more particle movement, the more contact they're going to have, and thus it increases the solubility, the amount it will dissolve. The solubility is a specific amount for a specific temperature. So let's look at what we mean on that. So the more rapid motion of the solvent molecule leads to an increase in the collisions, and therefore it will dissolve faster. So if you had hot coffee versus cold coffee and you added sugar, it will dissolve faster in the hot coffee rather than in the cold coffee. And that's the general rule. We're going to look at a graph here in a little bit, and I'll talk about that. So the particle size, I used the term of a cube versus granules. So the smaller the particles, and this is a key concept right here, the smaller the particles, the more exposure it has to the molecules of the solvent, and therefore it will dissolve faster. So if you have a large cube, it's going to take a lot longer because it's a surface phenomenon. Dissolving is a surface phenomenon. So it has to have contact with the solvent molecules in order for it to dissolve. So the rate at which a solute dissolves also depends on the size. So if you have a cube, it's going to take a lot longer than the granules will. So here's a checkpoint question. Which of the following will not speed up the rate at which a solid solute dissolves? So we look at A here, increasing the temperature. Well, we know increasing the temperature will increase how fast something dissolves. Stirring the mixture, that's called agitation. We know that that increases. Crushing the solute, well, that makes finer particles. That also increases. So those first three are true. That leaves decreasing the temperature. In general, if you decrease the temperature, it's going to take a lot longer for something to dissolve. And that's what it's telling us right here. All right, let's talk about solubility. We've mentioned it now, so let's actually define it and understand what we're talking about. How can you describe the equilibrium in a saturated solution? So let's talk about saturated, unsaturated, and supersaturated. So what is happening in this figure right here? in this figure here, you have some water in this beaker. And if you notice on the bottom, you have some solid there. It's a crystalline structure. It's an ionic compound that you see here. And what you see noticing solvation means some of this, as you see the arrow, is dissolving. And as some of it is dissolving, some is coming out of solution and crystallizing. So it is in a state of equilibrium. So equilibrium is not static. Static meaning that no more dissolves and no more crystallized. There's no hard, fast rule on that. It's called dynamic. So as some dissolves, what's in solution will crystallize. It just stays at that. So the net amount dissolving cannot increase. So whatever is dissolving, some other is crystallizing. So that's what this is signifying right here. So particles move from the solid into solvation and then into the solution. Some dissolved particles move from the solution back to the solid, and that is what equilibrium is. So let's define saturated. A saturated solution, this is really important, so please jot this down. A saturated solution contains the maximum amount of solute for a given quantity of solvent at a constant temperature and pressure. For a solid, the pressure really doesn't matter, but nevertheless, please get this definition down. We'll talk more on the pressure and how it affects solid solute. It doesn't, but let's talk about it. So a saturated solution. So if you saw a beaker, we see this beaker here, but say we have this beaker right here, and it has this liquid in it. And you notice there is a little solid formation on the bottom right there. That tells you that it is a saturated solution. It can't hold anymore, so therefore it's in a dynamic equilibrium with the solid solute that is on the bottom. So saturated solution, that's a clue. When you see particles on the bottom, that tells you it's saturated. It cannot hold any more of that solute at that particular temperature. Real important term. In a saturated solution, a state of dynamic equilibrium exists between the solution and any undissolved solute, provided the temperature is constant. Because if you increase the temperature, now more of it is going to dissolve. So solubility, we mentioned this, we just talked about it. What is that definition? So please get this right here into your notes, solubility. The solubility of a substance is the amount of solute that dissolves in a given quantity of solvent. So that's the dissolving agent is a solvent at a specific temperature and pressure to produce a saturated solution. The solubility is in many times grams per 100 grams of solvent. Grams per 100 grams of solvent. This is going to be something called molality. We're not going to really talk about molality, unfortunately, because of time. That would have been in 16.3, which we will not be covering. Sometimes the solubility of a gas is expressed in grams per liter, and that we're going to talk about at the end of today's lesson, and that's Henry's law. Solubility is grams per liter. So solubility, really important, and it is at a specific temperature. So a solution that contains less solute than saturated, meaning if you've seen a jar and it has some water in it and there's nothing in the bottom there, you could say that's unsaturated. Now that you have to tell, because it could be supersaturated, and we're going to define that here in a second. So the way you would tell if this is unsaturated, you would take a small amount of the solute and drop it in there. And either stir it or shake it or in some way agitate it. And then if you see that it dissolved, that tells you that that solution was unsaturated. If you drop that little bit of solute in and all of a sudden you see a large amount of precipitate take place, that means it was supersaturated. We'll define that next. But unsaturated means that it can still hold more solute. The clue is when you look at there is nothing on the bottom. It is completely liquid. There's no solid solute on the bottom. And that is the clue how you know that it's unsaturated. If additional solute is added to an unsaturated solution, it will dissolve. And that is the key point that I was trying to make. So some liquids, for example, water and ethanol, dissolve in each other. It doesn't matter how much. If you have alcohol and water and you pour it into one another, it's infinite amount. It doesn't matter how much. And that's called miscible. Two liquids are miscible if they dissolve in each other in all proportions. So that is miscible. Please make sure you make note of that. Alcohol and water is a great example. You can pour any amount of either, and they will always dissolve together no matter how much. That's called miscible. So now if you have something that's immiscible, unable to dissolve, so a liquid that are insoluble in each other are immiscible. Oil and water is an example. Once again, we mentioned this prior. You could put it in there, shake the container up, set it down, and all that's going to end up happening is it's going to separate into layers because it is immiscible, unable to dissolve in each other, or insoluble is another word. That's another key term, so please make sure you notate that. So checkpoint question. The solubility of a substance is often expressed as which of the following? So think about what we just talked about. All right, let's look at A, grams of solute per 100 liters of solution. We never talked about that, so that's not it. Grams of solute per 1 centimeter cubed of solvent. We did not talk about that either. Grams of solute per 100 grams of solvent. That's what we talked about. So the answer should be C. Grams of solute per 100 grams of solvent. And that is a different term, which I said we would not be going into in talking about. Factors affecting solubility. What factors affect the solubility of a substance? Factors that affect solubility. All right, so temperature affects the solubility of solids, liquids, and gaseous solutes in solvent. Both temperature and pressure affect the solubility of a gas. So that's real important. So what can affect a solid? The solid and a liquid, temperature affects, but pressure has no effect. When you talk about a gas, temperature and pressure effect. Really important. So please make note of that as we go into this section right here. So temperature, the solubility of most substances increase. So the solubility increases, goes up as the temperature goes up in most cases. In most cases, it does. All right. When you look at this graph here, for a few substances, it decreases. So here we have all these common ionic compounds that we are aware of. And then we have here your bitterzine, sulfate, 3-sulfate. That actually decreases. Look at that, how the solubility decreases as the temperature goes up. So it's actually more soluble in cold than it is in a hot solvent. So that's an exception. Look at NaCl. It pretty much is constant. It doesn't matter if it's increased in temperature. It just holds constant. And that's grams per 100 grams of water. And here is just another solubility list and temperature and how temperature does affect it. So let's talk about supersaturated solution, supersaturated solution. So you heard me mention it previously. A supersaturated solution contains more solute than what it theoretically can hold at a given temperature. So that would be this solvent, and you put in more of the solute than what it actually can hold. So that is called supersaturated. Once again, if you have this container here and there's nothing on the bottom, You take a little bit more of the solute and you drop it in. If you drop that little bit of solute and it disappears, that means it was an unsaturated solution. But if you drop that little bit of solute into that solution and all of a sudden you have this formation of a precipitate, that tells you it was a supersaturated solution. We're going to look at some pictures of that. The crystallization of a supersaturated solution can be initiated by a very small crystal called a seed crystal. So if this right here was the solute that you were going to drop in, they call that a seed crystal. And that just means a little bit more of the solute is dropped. And let's look at an example here. So here you have this right here, this boiling flask right here. And you don't know if it's unsaturated or supersaturated. There's nothing on the bottom, so those are the only two options you have. There's no solid solute on the bottom, so you know it's not saturated. So it's either unsaturated or supersaturated. So you take a little bit more, which you see right here, a little bit more of the solute, and they call it a seed crystal, and you drop it in. If it would have dissolved, that means it was unsaturated solution. But when they drop it, look at what happens automatically. A formation of the crystalline solid is dropped out of solution. So it crystallizes rapidly. That tells you when you see that occur, that solution was supersaturated. Temperature. The effect of temperature on the solubility of gases in liquid. So that's important. The effect of temperature on the solubility of gases in liquid solvents is opposite that of solids. We're going to talk about that. So let's just do a quick recap real fast. So if I have a solid solute, or a liquid, temperature increases the solubility. Temperature up, and that's for the most part, because there's that one that we noticed that it actually decreased. Now, when you talk about a gas, well, let me back up here a second. Solid solute and liquid solute, the temperature affects the solubility. Pressure does not. Pressure does not affect the solubility of a liquid or solid. Think about why. The pressure you'd be applying would be above the liquid. It doesn't affect anything inside that liquid unless it's a gas, and that's the key point here. So a gas solute is affected by temperature and by pressure. So the solubility of a gas in a liquid solvent is affected by both temperature and pressure. So that's an important note to get down into your notes, please. So change in pressure has very little effect on the solubility of solids and liquids, so it doesn't affect it. But the pressure strongly influences a gas. Gas solubility increases as the partial pressure above increases. So if you have this container, you have a liquid here, and you have another container here. You have this same liquid, same temperature. If you applied greater pressure, the solubility is going to be more of that gas in that liquid. If the pressure is lower, that means the solubility of the gas will be lower. So it is directly proportional to the pressure above the liquid. Soda is a great example of this. Carbonated beverages are a good example. These drinks contain large amounts of carbon dioxide dissolved in water. or the sugar solution or diet solution, whatever it is that they're making the soda out of. So what do? They pump carbon dioxide into the container before they put the lid on. And what happens is it forces the gas into the solution. When you open it up, that's why it fizzes. And that's why if you shake it up, now you can blow the top when you open it. So dissolved CO2 makes the liquid fizz and your mouth tingle when you drink it. That's why people like to drink soda. So the bottles are under high pressures of carbon dioxide, which forces large amount of gas into solution. So it dissolves in the solution. So when the container's open, the partial pressure above the liquid decreases. That's why if you open a jar of soda, a bottle of soda, and you just leave it sit, you come back later with no lid on it, all the gas will eventually escape. Why is it going to escape? Because there's no more pressure above it. So when you put the lid on, some more of the gas will escape, but it's trapped. So now it's going to keep pressure inside of that bottle. So immediately bubbles of CO2 form and then it escapes from the open bottle. So pressure, how is the partial pressure of carbon dioxide gas related to the solubility of carbon dioxide in a carbonated beverage? It's directly proportional to it. And that's what Henry's law is. So the relationship is described as Henry's law. Please write this down. States that at a given temperature, the solubility of a gas, which solubility is labeled as S, of a gas in a liquid is directly proportional to the pressure above the liquid. So that's S and P. So to be directly proportional, you know it's going to be S over P. S over P. That tells you it's going to be directly proportional. So as the pressure of the gas above the liquid increases, the solubility increases. As the pressure decreases, the solubility decreases. And here is Henry's law. S1, P1. So solubility 1, pressure 1 equals solubility 2, pressure 2. And the best way to solve problems with this, and we're going to look at several examples to write it out as S1, P2 equals S2, P1. And that way you can isolate. So the solubility is going to be in grams per liter. So solubility of a gas at pressure 1 and the solubility at pressure 2. So let's look at an example. So if the solubility of a gas in water is 0.77 grams per liter at 3.5 atmospheres, 3.5 atmospheres of pressure, what is its solubility in grams per liter at 1 atmosphere? So the pressure falls. So that would make sense even before we solve this. The pressure is going to go from 3.5 to 1. It would make sense that the solubility falls. And that's what we should see happen here. So once again, in these, we don't change anything. We always write down everything given. And that's what they do right here. And then they take their formula, they isolate it, and notice it is what happened. It is less. It's 0.22 grams per liter. And initially, if you look at what was here, initially pressure 1 was, solubility was 0.77 grams per liter. So it fell when it went from 3.5 atmospheres to 1, which follows and makes sense. So, checkpoint. Explain why an open container of a carbonated beverage is more likely to go flat sitting on the counter than in the refrigerator. So, think about this. So, if we had a liquid or a solid, so if we had a liquid or a solid solute, and we wanted to dissolve it. For the most part, if our temperature goes up, the molecules are moving faster, so it will dissolve more, so the solubility went up. But when you deal with a gas, I'm going to put G for gas here, as you increase the temperature, now the molecules are moving faster, which means they're striking the gas particles and allowing them to escape. So the solubility actually goes down for a gas in higher temperature. So colder temperature, so for gas, if the temperature is low, the solubility is actually going to be higher. Think about why. If you have a liquid and you have the temperature low, that means the molecules are not moving as fast. So they're not going to strike the gas molecules that are being dissolved in it at a faster pace, which means more can go in it without being struck and coming out. So that is a little different than a liquid and a solid because, like we said, as the temperature goes down, the solubility goes down for them. It's opposite when you talk about a gas. So please write this in your notes. This is really important. So thinking about this, which is more likely to go flat? Something on the counter or the refrigerator? Well, the counter is warmer, so the solubility is less. So that's the one you should have done. The solubility of a gas in a liquid increases as the temperature decreases. So more carbon dioxide will remain in the solution in the colder refrigerator than it would be on the counter. So the one on the counter would go flat fastest. So now let's look at some solving, some Henry's law solving. So let's just write down Henry's law here. We have S1 over P1 equals S2 over P2. And I showed you the best way for me anyways, to write this is S1 P2 equals S2 P1. Now I can write my variables and isolate what I'm solving for. So I'm going to come over here and write down some of these. So I have S1 P1, S2 P2. And I'm going to write down all my variables. So the solubility of methane, CH4, at 20 degrees Celsius and 1 atmosphere, so my pressure one is 1.00 atmospheres. And its solubility is 0.026 grams per liter. If the temperature remains constant, what is the solubility at 0.60 atmospheres? So the pressure is 0.60 atmospheres. So my pressure fell. It should make sense to you that before I even calculate it, my pressure fell, so my solubility should fall. So we're going to isolate and solve for solubility too. So that's going to be divided by P1, and I'm going to cross that off. So solubility 1 is 0.026 grams per liter. My pressure is 1.00 atmospheres, and I'm going to divide that by that 1 goes on the bottom. This here is your P2 goes here, which is right here, your P2. So this is 0.60. Please make sure you don't make that mistake right there. And this is atmospheres right here. So your atmospheres cancel. So now I can plug this in. So I'm going to go 0.026 times 0.60, and I'm going to divide that by the 1, which is my P1. And that is, so my solubility, and I have, because I have here only 2 sig figs right there, my solubility is going to be 0.016 grams per liter. And that is my answer, solubility. So solubility 2. So notice what happened. The pressure decreased, my solubility decreased. So that makes sense. All right, let's look at another one. The solubility of a gas is 0.68 grams per liter at 25 degrees Celsius and 1 atmosphere. What pressure will the solubility be 0.98 grams per liter if the temperature is held constant? Let's just analyze this real quick here. So what happens is my temperature is constant, my pressure is given to me, but it wants to know what the pressure is going to be if I go from 0.68 to 0.98. So my solubility increase, it should make sense that I'm looking for a higher pressure. So let's go ahead and start this. Let's write down. So we have S1 over P1 equals S2 over P2. And I like to separate them out. So I have S1 P2 equals S2 P1. And now come over here. So I have S1 P1 S2 Hang on one second, ladies and gentlemen. There we go. My pen seems to have stopped working for a second. S2 and P2. So when I look at what here I have, what I got here, 0.68 grams per liter, and my pressure is 1 atmosphere. It wants a solubility of 0.98 grams per liter, and I'm solving for what my secondary pressure is going to be. So I'm going to come over here and dissolve and divide by S1, and that gets rid of it here. So I'm looking for P2. So solubility 2, so I'm going to plug this all in. Solubility 2 is 0.98 grams per liter times pressure 1. Pressure 1 is 1.00 atmospheres. And I'm going to divide that by S1, which is 0.68 grams per liter. Grams per liter are canceled. Now I can solve. So I'm going to go 0.98 times 1, which is 0.98, divided by 0.68. So now pressure 2 is going to equal, and I have to be at 2 sig figs, 1.4 atmospheres. So my pressure went up. So I'm now here 1.4 atmospheres. So that is how you actually do the solving using Henry's law. Henry's law is pretty important. That's how you calculate your solubility of a gas. All right, so that is it, ladies and gentlemen, on 16.2. And there is our formula of Henry's law. So tomorrow's lesson, we're going to start talking about molarity. That's what I'm going to make my focus on. Molarity is how many moles of some solute are in liters of solution. So moles of solute and liters solution, and that equals the big M, which is molarity. Molarity is really important. So if you're given the molarity, you can calculate the moles based on the liters you have and vice versa. So molarity is a way that we can work with aqueous solutions. And we're going to do stoichiometry. We're going to do dilutions. So please, I wanted to just introduce this right here to you because that is a precursor to what we're going to be doing tomorrow, is calculating molarity. Molarity of a solution is the moles of solute in liters of solution. From that, we can get dilution and we can do stoichiometric calculations. But today we did learn Henry's law. You did some calculations with me on that, and you got some notes. So we have saturated, solubility, unsaturated, miscible, immiscible, supersaturated, and Henry's law. And ladies and gentlemen, that is it. So please, I hope you took some good notes today. And you have an assignment that I loaded in RenWeb and Moodle for you that is 16.1, numbers 1 through 9. So work on trying to get that done. It's due Monday at 8 p.m. So Monday we'll have 16.2 and more practice problems as bell work. So thank you for watching. Go in peace.